Hi Bobcats. In this video we're going to turn our attention away from acids and bases and look at a different type of equilibrium situation that exists in aqueous solution, which is solubility equilibria. We're going to introduce a new equilibrium constant, KSP, and see how we handle problems that include KSPs. Our objectives include explaining the difference between solubility and the solubility product constant, the KSP, and also starting to solve solubility equilibrium calculations using KSP. The solubility product constant, or KSP, is a value that you will find tabulated for all of those compounds that back in Gen Chem 1 we classified as being insoluble. Well, it turns out that even insoluble compounds are soluble in water, generally to a very, very tiny extent. A great example of that is calcium carbonate. This picture of the limestone formations that you'll find in caves like Natural Bridge Caverns. Carlsbad Caverns is real close to where I grew up. So at any of those places, those formations are created because calcium carbonate, also known as limestone, will actually dissolve in water to just a little teeny tiny extent. And as that water moves through the ground, the calcium carbonate will be deposited in these really interesting formations. We're going to write the equation for that dissolution process. So we'll have, as an equilibrium, so we'll have the solid on the left and then the separated ions on the right. And then when we write our KSP expression, we leave out the solid. Only the aqueous ions will be included in the KSP expression. Let's work a couple of examples where we just write the KSP expressions for these compounds. Now, when these compounds dissolve in water, they are going to produce the aqueous ions. So we need to first start by writing what that reaction will be. And so let's see, calcium fluoride will give us Ca+2 ions, right? Because calcium's an alkaline earth, it's in group 2. And then that will also give us 2 fluoride ions because fluoride is a monatomic ion. That subscript of 2 is there just for charge balance so that we have 2 negative ions from fluoride to balance the 2 positive ions, the 2 positive charges from the calcium ion. And one more thing to note in here, the calcium fluoride is a solid. So when we go to write the KSP expression, we will write just the products because the reactant is a solid. And so we will write Ca+2, and it has a coefficient of 1, so that goes to the first power, and then times fluoride ion squared because the fluoride ion has a coefficient of 2. Well, we were writing all of the Ka and Kb expressions. We didn't have to deal with any coefficients, so all of the powers were 1. Now that we're working with KSP expressions, we will have more coefficients and consequently more exponents. Now, what I'd like for you to do next is to write the equations and then the KSP expression for silver sulfate and for calcium phosphate. So pause this video, write those out, and then as soon as you have them written out, restart the video. All right, let's hope that you've written all of these out now. Silver sulfate. Now, remember, polyatomic ions will stick together when they dissolve. So that sulfate will dissolve up as a sulfate ion. The silver is a +1 ion, and we have 2 of them. So we'll have 2 silver aqueous ions plus the sulfate aqueous ion. So 4 minus 2. And so our KSP expression will be silver ion squared multiplied by sulfate ion to the first power. For calcium phosphate, oh whoops, I forgot to label that as a solid. For calcium phosphate, that will be a solid, and as it dissolves, we will get 3 Ca+2 ions and 2 PO4 minus 3 ions. And our KSP expression will be equal to calcium cubed multiplied by phosphate squared. And I just realized I'm writing the wrong arrows. These should all be equilibrium arrows, not one-way arrows. All right, there we go. For this clicker question, we're asked to determine which of the following salts is the most soluble. Now, what we're given for each of the salts is the value for the KSP. The most soluble should correspond to the largest KSP value. Now, that statement that the biggest KSP should correspond to the most soluble is only good because we get an equal number of ions from each one of these compounds. From whether it's PCl2 or Ag2CrO4, we're getting a total of 3 ions. In the case of silver chromate, we're getting 2 silvers and 1 chromate. In the case of lead chloride, we are getting 1 lead and 2 chlorides. So either one of those cases, we're getting 3 particles total. If we were getting a different number of particles from the different choices, we would have to do a little bit more detailed calculation, and we'll do that in a later example. But for right now, the most soluble is going to correspond to the largest KSP, and the largest number for KSP is that first one, the 1.7 times 10 to the minus 5. So lead chloride will be the most soluble of these compounds. All right, so one of our objectives was to distinguish solubility from the solubility product. Well, solubility is a measure of how much solute will dissolve to make a saturated solution. Think back a couple of chapters to where we looked at unsaturated versus saturated. So solubility is how much stuff will dissolve to make a saturated solution. It's typically expressed in units like grams per liter or moles per liter. I think in the previous chapter where we were looking at this, it was grams of the solute per 100 grams of water. That's another unit that gets used for solubility. And solubility can change with conditions. We saw how the solubility of a solid in a liquid changes dramatically with temperature for some species, so that if you increase the temperature, the solubility in general will increase. Now, the solubility product is an equilibrium constant, right? It's the equilibrium constant for the equilibrium established between an ionic solid and its saturated solution. And we're going to put that subscript SP on this equilibrium constant to distinguish it from other types of reactions. Being an equilibrium constant, it's unitless. And KSP will be a constant except for temperature. And so how is that different from solubility? Well, both solubility and the KSP can change with temperature, but KSP remains constant whether we're talking about an acidic solution or a basic solution or other components being present in the solution, whereas solubility can change dramatically if we change the pH or we change other things that are dissolved in the solution. Let's look at this first numerical example. It says we're trying to find KSP from solubility data. A saturated solution of magnesium fluoride in contact with undissolved solid is prepared at 27 degrees C. Remember, that experimental setup is how you typically identify that you have a saturated solution. You still have some solid sitting there, so you know it's saturated, because if it were unsaturated, that solid would just keep dissolving. But the fact that solid is there means it is completely saturated. So we've already reached equilibrium here, and we are told that the concentration of magnesium ions in the solution is 1.2 times 10 to the minus 3rd molar. And we're asked to find the value of KSP. So let's take a look at our reaction. Our reaction will be magnesium fluoride solid in equilibrium with magnesium ions and 2 fluoride ions. If we're going to set up an ice table here real quick to look at that, we're going to squiggle out magnesium fluoride since that doesn't appear in our KSP expression. Initially, we don't have anything dissolved. That's the model that we're using. You add the solid to your water, you start stirring it around, and then some magnesium will dissolve, so we'll call that plus X for the Mg plus 2. And then for every Mg plus 2 that we get 2 fluoride ions. So our change in fluoride will be plus 2x. So at equilibrium we'll have x and 2x. But here's the kicker. We already know what x is because it told us that the concentration of magnesium ions is 1.2 times 10 to the negative third molar. So when we look at our KSP expression, that's going to be equal to magnesium ions times fluoride ions squared. And so if we start plugging numbers in here for magnesium, we have 1.2 times 10 to the negative third. For fluoride, and I'm running out of room, so I'm going to write that just underneath it, we have twice as much because it's 2x, so that becomes 2.4 times 10 to the minus 3, and then of course we have to square that. And so let's see if I can run this through my calculator. 1.2 EE3 negative times 2.4 EE3 negative squared. And let's move that to scientific notation. I've got 6.9 times 10 to the negative 9 for KSP for magnesium fluoride at this temperature.